Projectile motion is the study of motion now, not in one dimension, but now in two dimensions. So when we have an object that is moving both vertically as well as horizontally. That's going to be an example of projectile motion. Some important things is that with projectile motion, the only force, and we haven't talked about forces yet, but the only force that's really acting on objects are gravity. So there's no thrust, there's no engine. It's once something is moving through the air with the only thing acting on it being gravity. What we have to understand with projectile motion is that we can treat the X and Y motions as independent. They don't affect one another. And so what we'll see is when we work through problems, we can treat our X motion as something and separate that from our Y motion. Specifically, the X motion is going to be constant, and we'll see an example of it as to why. So we're going to treat X velocity as a constant velocity. So whatever it starts with, there's no air resistance, there's no drag. So whatever the X velocity is at the beginning is going to remain constant. The Y motion, however, is going to be accelerated, and it's going to be accelerated due to gravity. So our acceleration is going to be little g, which again is going to be 10 meters per second squared. The one thing that we can take back and forth between both our X and our Y motion is time. Time's going to be the one thing that we can use in both circumstances because time is going to be the same for both my horizontal motion, which is the X, and my vertical motion, which is the Y. The first example we're going to look at is imagine riding in a car or on a wagon and you have a ball in your hand. If the wagon's at rest, we can simply toss that ball straight up and down, and then we're going to catch it exactly where we let it go. Well, what if that object is now moving, or that wagon is moving, right? Now we're going to have projectile motion where if we're moving, we can still throw the ball straight up and down, but we're going to catch it at a different location. Why is that? Now we don't have to think about throwing it this way. We just have to worry about tossing it straight up and down because we're still going to catch it exactly where we released it. However, we're going to be further in the X direction. So let's think about this. If the wagon is traveling at 3 meters per second, okay, that means the ball, when we release it, is also traveling to the right at 3 meters per second. Okay? When we throw it straight up, this velocity stays constant. However, our ball is going to take some path that looks like this for us then to catch it at the same location. Okay? Let's say we throw it upwards at 4 meters per second. Right? So now what we're going to do when we work through these problems is we're both going to have an X motion and a Y motion when we identify the variables that we're dealing with. So our initial velocity in the X, our initial velocity in the Y, we can have displacement in the X, final velocity in the Y. We can have time, acceleration and displacement in the Y. Those are basically the variables that we could have in either one. What we know is that this is 3. We know that this is going to be positive 4. We're going to say up is the positive direction and to the right is the positive direction. So my final velocity, if I'm going to catch it at the same height, is going to be negative 4. My acceleration would be negative 10. And the other thing, forgot this one. The other thing would be time. And time is the thing that we can have for both X and Y motion. What I can do then is I can work through and figure out my displacement. If I don't have time, I can still figure out my displacement in the Y direction. I could then figure out how far the ball went here, because once I know displacement, I can solve for time, and we can work through all this. So if we look at this, let's try to find time first. Well, to do that, I'm going to use my Y motion. So I'm going to use my blue marker, right? And I'm going to say velocity equals velocity initial plus acceleration times time. So velocity minus velocity initial equals acceleration times time. So velocity minus velocity initial over acceleration equals my time. Negative 4 minus 4 divided by 10 That's a negative 10. Right, so that's my time. That is the same time in the x motion. My displacement actually with this would be 0, right? Because I catch it at the same point of which I released it. So my total displacement in the y motion would be 0. And then I could figure out, well, how far did this ball actually travel in this direction? Well, I can use my constant velocity idea for my x motion, and that is saying that basically velocity equals displacement over time. Displacement then is velocity times time, which would be 3 times 0.8, which is 2.4 meters. So my displacement in the y direction is 2.4 meters, okay? What we can understand though is that when I actually toss it up, I toss it up with 4 meters per second. The ball is traveling already this way because the car is moving at 3 meters per second. So the total velocity here, we could do vector addition and say 3, 4, and figure out what my total velocity is there. We create a right triangle here, so we can just use Pythagorean's theorem, and if we can see a quick 3, 4, we know that my total velocity would be 5 meters per second. So even though the ball was only thrown up by myself at 4 meters per second, because the car was actually traveling at 3 meters per second, the ball itself is traveling at 5 meters per second up at an angle. Right? If we wanted to, we could solve for that angle using tangents, and we could work through that just like we would when we're working with vector addition. So there's two main types of problems we're going to work through when dealing with projectile motion. The first one, what I consider, is called a cliff problem, where something is at a vertical height and they're moving at a velocity in the x direction, and they're going to launch themselves off the cliff. So we can say that the cliff is maybe 100 meters high and that they are driving at a velocity equal to 60. Things you might run into: how long is the car in the air? How far over here do they hit? What is the total velocity when they actually hit the ground? So what we can look at is both its x motion and its y motion independently again, right? So we're going to identify the velocity in the x, we have displacement, and we have time. We have initial velocity in the y, we have final velocity in the y, we have acceleration, and we have displacement in the y. So things we can identify. My initial velocity is 60. I don't know my displacement yet. I don't know my time. My initial velocity in the y. Well, because it's only moving horizontally, my initial velocity is 0. It's just like something that's being dropped, right? My acceleration is going to be negative 10. My displacement would be negative 100. And again, time is the one thing that I don't have. Now again, we draw it down there because time is the one thing that I can take back and forth between x and y motions. So the first thing I can imagine is, let's imagine this car isn't actually being launched off the cliff. It's just falling straight down, right? Because that time of just falling straight down is going to be the same as it launching off the cliff. So we can solve for time first. To do that, I'm going to use delta y equals velocity initial times time plus 1/2 at squared. This goes to 0. So I get 2 times my change in y over my acceleration equals time, and we square root that. All right, so that's how I'm going to solve for time in this example. So that's going to be 2 times negative 100 divided by negative 10 square root. That's 20, the square root of 20, and that's going to be 4.5 seconds. Now the nice thing is that I can also bring that over here. That's in the air for 4.5 seconds. Okay? So now, what I know is this velocity is constant. So I can figure out how far away from the cliff does it actually hit 4.5 seconds later. Well, I can use my constant velocity equation for the x, where velocity is displacement over time. I could then solve for displacement, which is velocity times time. And that would be 60 times 4.5. 270 meters. So that's how far from the cliff it lands, 270 meters. Right? Now, if I were given 270 meters, I could work backwards and solve for time. Okay? So I'm not saying this is always the pathway we're going to work through this, but this is examples of how we would work through the thought process of this problem. What also I will solve for now, real quick, is my final velocity, as well as the total velocity when it hits here, because when it hits here, it's going to look like a path like that. And so it's actually going to be moving down at some angle, and we're going to solve for that total velocity there. To solve for my final velocity in the y, I can just use initial velocity plus acceleration times time, because I now know time. This again is 0, so my velocity in the y is negative 10 times 4.5, which is negative 45 meters per second. And then, again, down here, if I wanted to find my total velocity, right, well, I know that this is 60. I know that this is negative 45, not very well drawn to scale. But because it's vector addition, we have a velocity plus a velocity, I can do my Pythagorean theorem. And I can do velocity in the x squared plus velocity in the y squared equals my velocity total squared. So that's 60 squared plus 45 squared, square root that, which means I would hit the ground at a velocity of 75 meters per second. Okay? So I'm actually going to be traveling faster than 60, faster than the 45, right? At 75 meters per second. Again, if I wanted to find the angle with that, I could do the inverse or arctan and determine what the angle it's actually going to be hitting the ground with. In our next video, I'll just show a quick example of what I call a cannon problem, which is the other common form of the projectile motion problem that we'll run into in physics.